Could the chain of recent tremors across the Philippines be more than coincidence? Late September through October of the year 2025 saw a flurry of seismic unrest, a magnitude 6.9 quake beneath Cebu on the 30th of September, followed by a magnitude 7.4 off Surigao del Norte on the 10th of October and a second magnitude 6.7 hours later. Dozens of aftershocks continued to rattle the region for weeks. Across the archipelago, speculation began to rise like waves across the sea. Could these tremors somehow be linked to the Apolaki Caldera, the world's largest known volcanic depression lying silent and submerged beneath the Philippine Rise? Might the planet's largest caldera be stirring, millennia after it last breathed fire? Or are these simply tectonic murmurs, echoes of deep Earth mechanisms operating along one of Earth's most violently active subduction zones? For a question so heavy, science begins not with speculation, but with mechanism. The Philippines sits at a tectonic crossroads, the collision of the Philippine sea plate with the Sunda and Eurasian plates. In this crucible, crust is forever being born, folded, dragged, and recycled. The country's geography itself testifies to this constant motion. Chains of volcanic arcs, deep oceanic trenches, and earthquake scars stretch across the islands. When the ground shakes, the cause usually lies in the endless tug-of-war beneath, not in hidden magma surging to the surface. The first tremor, a magnitude 6.9 under Cebu, struck at a depth of roughly 10 kilometers, about 6 miles. The second, the devastating magnitude 7.4 near Davao del Norte, originated much deeper at 58 kilometers, around 36 miles. In between and afterward came a torrent of smaller shocks, magnitude 5.8 east-southeast of Santiago, magnitude 4.9 near Luzon, magnitude 5.0 southeast of Bourbon, each a fragment of the greater tectonic pulse. By mid-October, more than 120 tremors had been logged across the archipelago. To an untrained eye, this sudden burst of energy might seem ominous, perhaps even a signal of magma rising from the deep. Yet the pattern fits precisely with what geophysicists call stress redistribution. After a major rupture, such as the DA-VAO event, the crust does not settle immediately. Instead, its internal stresses shift along adjacent faults, awakening nearby segments that have been quietly accumulating strain. Like dominoes toppling across a fault network, the energy cascades through the lithosphere, sometimes for weeks or months. The Philippine Trench. The eastern boundary of the Philippine sea plate is among the planet's deepest scars, plunging more than 10 kilometers over 6 miles below the ocean's surface. Here, the dense oceanic crust dives westward beneath the Philippine mobile belt in a subduction process that has persisted for tens of millions of years. The same process fuels the fiery chains of volcanoes across the archipelago. When the subducted slab descends, it releases fluids from hydrated minerals, triggering partial melting in the overlying mantle wedge. The molten material then rises, feeding volcanoes from Bicol to Mindanao. But the Apolaki Caldera lies far from this fiery front. Situated roughly 250 kilometers, 160 miles east of Luzon on the Benham or Philippine Rise, Apolaki rests atop a different tectonic story. The Philippine Rise is a massive underwater plateau, an ancient volcanic edifice built in the Eocene epoch, some 40 to 50 million years ago, when mantle plumes welled upward through a thin oceanic crust. Rock samples from dredging expeditions show basaltic compositions consistent with hotspot volcanism rather than subduction-related magmas. In essence, the Rise was once a colossal shield volcano system, perhaps several overlapping volcanoes whose eruptions were so extensive that they created an elevated dome over 300 kilometers, about 186 miles across. At its heart lies Apolaki, the giant lord in Filipino myth, a caldera roughly 150 kilometers, 93 miles wide, dwarfing even the Yellowstone caldera in the United States or the Toba caldera in Indonesia. To imagine its formation is to imagine an eruption so vast it defies comprehension. Trillions of tons of basalt expelled into the ocean, the crust collapsing under its own weight, leaving a circular scar that remains visible even after eons of sedimentation. How can such a system, thought long extinct, be suspected of any new stirrings? The answer lies in the psychological pull of scale. The larger a volcanic structure, the more we tend to imagine that it hides deep, slow forces still at work. Yet geologic evidence tells a different story. Since the Eocene, the Philippine Rise has drifted away from its hotspot source and cooled significantly. Thickened oceanic crust, up to 20 kilometers, 12 miles, in some regions, now acts as an insulating lid, sealing off whatever magmatic remnants once pulsed beneath. Without an external heat source, such as an active mantle plume, the remaining magma chambers would gradually crystallize over millions of years, transforming molten basalt into solid gabbro. Geophysicists model this process using conductive cooling equations. A magma reservoir 10 kilometers thick may solidify completely in as little as 10 million years under submarine pressure, especially when hydrothermal circulation draws heat away through cracks. Apolaki's last known eruptive phase likely ended between 26 and 48 million years ago, meaning the system has had ample time, many times over, to freeze into stone. Still, the human mind wonders. Can earthquakes at great distance awaken such a fossilized structure? The United States Geological Survey and other research institutions have examined numerous cases worldwide. The consensus is that earthquakes can only trigger volcanic activity if the volcano is already primed, that is, if molten material under pressure is close to erupting. Dynamic stress waves from an earthquake can jostle a magma body, inducing degassing or crack propagation, but only when that magma exists in a mobile, gas-rich state. If instead the reservoir is solid, or nearly solid, the passing waves merely rattle the rock. Apolaki sits nearly 3 kilometers, almost 2 miles, beneath the sea surface. The water pressure alone, around 300 atmospheres, further suppresses any explosive volatility. Former PHIVOLCS director Renato Solidum has stated plainly that Apolaki is geologically extinct, its last breath spent millions of years ago. No volcanic gases bubble from its rim, no thermal anomalies appear on satellite sensors, and no volcanic micro-earthquakes cluster beneath it. Yet the notion of reawakening persists, perhaps because the caldera's immense scale invites mystery. If Yellowstone could one day erupt again, why not Apolaki? The difference lies in internal heat. Yellowstone sits atop an active mantle plume whose thermal flux continuously recharges the crust with fresh magma. Apolaka's heat engine, in contrast, shut down tens of millions of years ago. Nonetheless, the connection between the recent Philippine quakes and deeper mantle processes remains scientifically fascinating. Each major earthquake alters the stress field of the entire region. The Philippine Trench, by thrusting downward, can influence how stresses propagate eastward toward the Philippine Rise. Some researchers have proposed that stress transfer through the subducting slab could, in theory, reactivate old fracture zones within the rise, perhaps creating minor seismicity along ancient faults. Such micro-quakes, however, are tectonic, not volcanic. They reflect the crust adjusting, not magma ascending. Moreover, the Philippine Rise's crust is anomalously thick for oceanic lithosphere, suggesting it once functioned as a microplate that detached from the main plate boundary dynamics. Its isolation from current subduction interfaces means that energy from recent earthquakes dissipates long before reaching Apolaki's base. Even if shock waves were transmitted, they would likely attenuate into harmless vibrations by the time they reach the buried caldera floor. Still, beneath this apparent calm, subtle processes continue, processes measured not in years, but in geologic epochs. Isostatic adjustment, for example, slowly reshapes the Philippine Rise as its dense volcanic roots cool and contract. Sedimentation gradually fills the caldera depression, while submarine currents carve channels across its rim. These quiet, persistent transformations are the true language of an ancient volcano's afterlife. And yet, mystery lingers. Could there be remnant magma pockets deeper than our instruments can detect? Could some fraction of the original mantle plume remain faintly warm, diffusing heat upward through the basaltic layers? Theoretically, yes, the lower crust may retain partially molten zones at depths exceeding 20 kilometers, about 12 miles. But without replenishment from below, these pockets cannot drive renewed volcanism. To explore this possibility, geophysicists often compare Apolaki to the Ontong Java Plateau in the Pacific, another massive volcanic province formed in the Cretaceous. Both share basaltic compositions and immense scale, and both now rest dormant. Deep seismic imaging of Ontong Java shows only solidified crustal layers, no active melt. Apolaki's structure, though less studied, likely mirrors that outcome. When scientists discuss the idea of the Apolaki Caldera reawakening, they are not referring to an imminent eruption, but rather to the subtle ways tectonic energy may migrate through lithospheric weaknesses. Beneath the Philippine Rise, the caldera's foundation rests on an unusually thick portion of oceanic plateau crust, estimated at 15 to 18 kilometers, or about 9 to 11 miles. This thickness grants it tremendous mechanical strength, explaining why it has remained dormant for tens of millions of years. Still, a powerful earthquake along the Philippine Trench has the potential to redistribute stress across the crust, flexing the overlying plateau ever so slightly. Modelling of such events shows that the resulting stress waves can sometimes reopen ancient fractures, but only if those fractures remain brittle or partially sealed. In Apolaki's case, geophysical surveys reveal minimal gravity anomalies and uniform seismic velocities, signs that its internal conduits have solidified into dense, impermeable rock. The pathways that once channeled magma from the mantle are now sealed by time itself. The subduction processes that shape this region continue relentlessly. The Philippine sea plate moves westward, rolling back as it dives beneath the Philippine Trench. This generates complex mantle flow beneath the region, yet tomography reveals that a tear in the descending slab south of the Philippine Rise redirects upwellings away from it. In many volcanic arcs, such mantle rearrangements can rejuvenate volcanism, but the Philippine Rise is an exception. Its lithosphere has long cooled and thickened, effectively sealing off the deep, magmatic plumbing that once fed its fiery origins. To restart such a colossal volcanic system would require either a new pulse of magma from a mantle plume or an episode of deep fracturing that allows molten material to rise again. Neither condition is currently present. The nearest active magmatic centres lie hundreds of kilometres to the south, near the Benham and East Luzon troughs, and none exhibit signs of thermal or compositional connection to Apolaki. After the eruption that formed the caldera some 48 to 50 million years ago, the vast depression began to fill with marine sediment. Core samples and seismic profiles reveal layered deposits more than a kilometre thick. This blanket of sediment now serves as both an insulator and a stabilizer, absorbing strain energy that might otherwise accumulate at the caldera's rim. Measurements of modern heat flow confirm that the Philippine Rise is a thermally mature region, with low values typical of ancient stable crust. The caldera has effectively become a fossil, preserved in extraordinary detail, but long past the era of magmatic activity. Comparing Apolaki to other massive submarine volcanic structures helps illuminate its nature. Its closest analogues are found in the Ontong Java Plateau north of the Solomon Islands and in Shatsky Rise to the northwest Pacific. These two were formed by enormous mantle melting events during the Cretaceous period, each producing vast basaltic plateaus that thickened the oceanic crust in short, violent bursts of activity. The similarity is striking. A brief geological instant of unimaginable energy, followed by tens of millions of years of quiet. Once cooled, these immense provinces become rigid, neutrally buoyant slabs that drift through time, largely untouched by the convulsions of surrounding subduction zones. Recent modelling of stress transfer after the Philippine earthquake indicates that the region east of the rupture zone, including the Philippine Rise, may actually be under reduced stress rather than increased strain. This so-called stress shadow effect occurs when an earthquake releases built-up energy, leaving adjacent crust temporarily relaxed. In other words, instead of destabilizing Apolaki's crustal lid, the quake may have further secured its stability. The same effect was observed after Japan's 2011 Tohoku Oki earthquake, when nearby areas experienced a measurable drop in tectonic stress. Over millions of years, thermal contraction of the oceanic crust produced cracks that initially increased permeability, but these fractures gradually filled with silica and sulfide minerals from hydrothermal fluids. The result is a dense network of sealed veins that act as metamorphic armor. Apolaki's seismic signature confirms this interpretation. A rigid basaltic framework overlain by layers of pelagic clay and carbonate sediment. Such a configuration makes any renewed ascent of magma physically impossible without an entirely new mantle, heat source and event far beyond the scale of regional tectonics. Nonetheless, some geodynamic models invite speculation. If a segment of the subducting Philippine plate were to detach, a phenomenon known as slab break off the resulting mantle, upwelling could, in theory, reheat the base of the Philippine Rise. This would take millions of years to develop, and even then the likely result would be small-scale intrusions rather than a catastrophic eruption. Oceanic lithosphere under compression tends to form fault-bounded ridges and minor volcanic cones, not explosive calderas. The forces required to reawaken Apolaki simply do not exist in the modern Earth. Seismic networks support this interpretation. Instruments operated by PHIVOLCS and international agencies detect no microseismic activity in the Philippine Rise, only background vibrations caused by ocean currents. These data confirm that the caldera is structurally inert. Yet scientists continue to monitor it closely, not out of fear, but to better understand how massive volcanic plateaus evolve and remain stable over geological time. Far from being a danger, Apolaki is a magnificent time capsule. Its structure preserves the memory of one of Earth's greatest magmatic episodes. The circular ridges, the deep central depression, and the distribution of dense rock all record the dynamics of an ancient mantle superplume. It serves as a blueprint for understanding how the planet's internal heat once erupted on a scale unmatched by anything in the modern world. Even planetary scientists draw parallels between Apolaki and giant volcanic shields on Mars, such as Olympus Mons, whose vast caldera collapse features mirror Apolaki's geometry. If you enjoyed this deep dive into the mysteries beneath our planet, don't forget to give this video a like, share it with your friends, and subscribe for more incredible Earth and space discoveries. Tap that hype icon to help this video reach more curious minds around the world. Your support keeps us exploring the unknown.